This video goes through matrix dilations. Now, a dilation is a linear transformation that either enlarges or shrinks the pre-image on the plane. Now, a dilation requires a center point and a scale factor. So that center point is where it's dilating from, and the scale factor is how much it's dilating by. So we can have three types of dilations. We can have a horizontal dilation, a vertical dilation, or a dilation from both axes. If we're looking at a horizontal dilation, it's from the y-axis. Okay, so it's stretching out from the y-axis. So if you look at your axes here, there's your y-axis. It's moving out from your y-axis. Okay, or it could be a smaller than 1 dilation, which means it's going to come towards the y-axis. So if you think about that, what's changing is your x value. Okay, so x is changing. The y value stays the same. All right, so if we look at this dilation matrix here, and there's different forms of notation. I have decided to go with DA1, where A is the dilation in X, and then the 1 is Y stays the same. So the dilation is A from the Y axis, which means my X value is changing. Okay, your Y value is staying the same. So that's why there is a 1 there. Okay, so if you think about it, you've got A001 times by XY. If you times across the row down the column, you're ending up with AX. So that X value is being multiplied by some factor A. And then your Y value is staying the same. Okay, and as I said, your A could be greater than 1, which means it's going to be stretched out from the original, or it could be smaller than 1, which means it's going to go closer to the y-axis. Now, our vertical dilation is a dilation from the x-axis. So if we're looking at our axes here, there's our x-axis. So now we're looking at the change this way. So in this case, the x is the same and the y is what changes. So I've decided to use a notation D1B. So the x stays the same, it stays as 1, which you can see in that matrix, but your y value is going to be changed by a scale of b. So again, if we multiply that dilation matrix by xy, we end up with x, by. So our y values is changing, our x is staying the same. Now, if we have a dilation from both axes, it's a dilation to the entire plane. So you've got an xy change. So you've got to change horizontally and you've got to change vertically. So when you look at the dilation matrix, you have an A and you have a B. So your X is changing by a factor of A and your Y is changing by a factor of B. Now, A and B could be the same. If A and B are the same, it's an enlargement or a reduction. So it's a similar shape. If A and B are different, then your object is going to be skewed. So let's look at an example. Determine the coordinates of the image of the point 3, -4 under a dilation of factor a half from the x-axis. So it's from the x-axis. So we've got a vertical stretch or compression. It's being multiplied by a half. So if it's a vertical compression or stretch, in this case, it's times by a half. So it's going to be compressed. Our x is going to be the same and our y is going to change. Okay, so let's look at our dilation matrix. We know our x is going to stay the same, but our y is going to change with a scale of a half. So our matrix is going to be 1, 0, 0, a half. So let's find our image point. It's going to equal our dilation matrix times by the pre-image, which is 3, -4. So doing that multiplication, do it by hand or use your calculator. Pretty straightforward. 1 times 3 is 3. 0 minus 4 is 0. So you've got 3. 0 times 3 is 0. A half times -4 is -2. So therefore, the image point is 3, -2. Now, if you compare, we started with 3, -4, and we've ended up with 3, -2. So you can see your x stays the same and your y has been times by a half. So that verifies that we've done it correctly. Let's look at the next one. Determine the equation, the image of the parabola with the equation y equals x squared, dilated by a factor of 2 from the y-axis. So it's from the y-axis. We have a horizontal, in this case it's times by 2, so it's a stretch. So we're multiplying by 2. So in this case, our x changes and our y is the same. So when we think about our dilation, our x is changing by a factor of 2 and our y is going to stay the same. So my dilation matrix becomes 2, 0, 0, 1. So you can see why I kind of like that notation in terms of the 2, 1, thinking about what's happening. It kind of helps understand what's going on. So our image is going to be our dilation matrix times by our xy. Two times x is 2x. 0 times y is 0. 0 times x is 0. 1 times y is y. So we've got our image of x is going to be 2 lots of x, and our image of y is going to be y. Rearranging this equation, x is going to be the image of x over 2. Go back to the equation we're starting with, which is y equals x squared, and replace with those values. So the image of y is going to be the image of x over 2 all squared, which is the image of x all squared. All over 2 squared is 4. So that's what we've got. Okay, run out of room. So therefore, the equation of the image is that. So you can see it's still a parabola. So if we verify it, we started with y equals x squared. So let's sketch that. And we ended up with y is x squared over 4. Okay, so before when 1 squared was 1, it's now going to be a quarter. When it was 4, it's now going to be 1. Okay, if you put 4 into it, 4 squared 16, 16 divided by 4 is 4. So that is our image. And what you can see is if this is the 0.24, this is the 0.44, so your Y value has stayed the same and your X value has multiplied by 2. So from here to here, your X values increase by 2. And you can see that with all of the points that I've put on. Okay, so it's a horizontal stretch. So notice that what you have to get is that the Y value stays the same, the X value has doubled. Let's look at a practical example. Jo has fenced a rectangular vegetable patch with the posts as follows. She wants to increase the size of the vegetable patch by a dilation factor of 3 in the X direction and a dilation factor of 1.5 in the Y direction. Determine where Jo should relocate the fence posts. So first of all, let's write a matrix for our veggie patch. So 0, 0, 3, 0, 3, 4, 0, 4. Now let's look at our dilations. This is a dilation of factor 3 in the X direction. So that means in a horizontal is going to be times by 3. And a dilation of 1.5 in the Y direction. So that's our vertical is times by 1.5. So with the times by 3, that's our X value that's going to change. And with the times by 1.5, that's my Y value that's going to change. So when we write our dilation matrix, our X is changing by 3, our Y is changing by 1.5. So we end up with 3, 0, 0, 1.5. So our image is going to equal that dilation matrix times by the matrix for our fence posts. Throw that on your calculator if you want, or do it by hand. There's lots of zeros, so it's not that difficult. So therefore, the new fence posts are located at A is 0, 0, B is 9, 0, C is 9, 6, and D is 0, 6. So if we go to our axes and just see how that looks, I'm going to put the original on. Then let's put our change. This is part B. And what you should be able to see is that in our vertical direction, we've times by 1.5. And in our horizontal direction, we've times by 3. So if you think about this coordinate here, if we look at C, it did have a Y coordinate of 4, and then it became 6, which is times by 1.5. Now let's look at the next part. It says Jo has noticed that the vegetable patch in part A is too long and can only increase the vegetable patch by a dilation factor of 2 in both the X and Y direction. Determine where she should relocate the fence post. Determine if this will give her more area. So there's another part of it to plant vegetables, and it says to explain. So now we're going the same dilation in both directions, and it's a factor of 2. So our dilation matrix is 2, 0, 0, 2. So our image is going to be 2, 0, 0, 2 times by where my original fence posts were. Multiply that out. So therefore, the new fence posts are at, for A, 0, 0, B, 6, 6, D, 6, 8, oh, C, that would be, and D is 0, 8. Now, the second part was, will this give her more area? Now, the area for part A, which we've already got in here, will be 6 times 9, which is 54 units squared. Now let's put on our next one. So 0, 0, 6, 6, 6, 8, and 0, 8. So you can see with that dilation being the same in both directions. So you've times by 2, times by 2. We have a similar shape, it's just enlarged. So my area for part B, part B. So I'll label that. Is going to be my 6 times 8, which is 48 units squared. So therefore, the farmer will actually have less area. And it's going to be 6 units squared less. To plant the veggies when dilating by 2 in both directions. Okay. Let's look at another example, our last example for dilations. Determine the image of the relation x squared plus y squared equals 4. So in my head, I'm already going, that's a circle, center, 0, 0, radius 2. It's dilated vertically by a factor of 2. And it says verify your solution by graphing on your calculator. So our dilation matrix, we're dilating vertically. So that way by a factor of 2. So that means our x is the same and our y is changing. So x will remain the same and y will increase by a factor of 2. So our image is going to be that dilation matrix times by my original x and y. 1 times by x plus 0 times by y is x. 0 times by x plus 2 times by y is 2y. Makes sense. Y is doubling. So from there, we have the image of x is x. The image of y is 2 lots of y. Rearranging that, y is going to be the image of y divided by 2. I'll rewrite that so you can actually see that image. So let's go back to our original equation. X squared plus y squared equals 4. Our image of, well, x is just the image of x. So we've got the image of x all squared plus our y is the image of y over 2 all squared equals 4. So the image of x all squared plus the image of y all squared over 4, because it's 2 squared, equals 4. Now, just note, we could use inverse matrices to also do this. So from this step here, you would go 1, 0, 0, 2 to the negative 1 times by your image would be give you your x, y. So you've pre-multiplied by the inverse. This matrix all to the negative 1, so the inverse of it is equal to 1, 0, 0, a half times by your image, your xy, and then you end up back at that point there. It's longer if you are tech-free, if you're not using your calculator to find the inverse. Now let's go to our calculators and check what we have.
So let's verify what we've got. In our graphing, it's a relation. So if we backspace, you'll get the option for relation, which means we can now go x squared plus y squared equals 4. And there's our circle. Tab to be able to put into our other equation, which was x squared plus y squared divided by 4. And that equaled 4. And what do we get? It's an ellipse. So you can see that our x coordinate has stayed the same. So that's the same that way, but our y coordinates have doubled. And that stretches the circle vertically, which turns it into an ellipse.
So let's put that on our graph. You should be able to draw your circle without going to your calculator. So that your x squared plus y squared equals 4. And as we found, our image is an ellipse. And again, you could have figured that out using your knowledge of dilations and realizing that it's your y value multiplying by 2 and your x value staying the same. So this 0, 2 is becoming 0, 4. Label that equation.